So here we are in part 3 of our chapter 2 lecture. We've talked about our addition and subtraction, and now we're going to talk about how computers perform multiplication and division operations. Now, both of these operations are far more complex than our addition and subtraction. They take longer to perform, they require more complex hardware. Really, we're going to cover just the fundamentals because the actual operation requires a pretty significant amount of math. If you've not had calculus, it is most likely just going to confuse you, which is fine. At this level that I'm presenting this course, I don't expect that maybe you've taken calculus yet. And so we're just going to talk about things at kind of the fundamental level so that you understand these operations and why they're complex and why they take more time on the microprocessor. So starting with shifting operations, right? Before we talk about how multiplication is performed in binary arithmetic, we're going to describe the arithmetic shift. So this treats the bit pattern to be shifted as our 2's complement value. In a shift operation, all of the bits of a word are shifted one place left or right. And so some computers can shift a string of bits more than one place at a time, which then creates the opportunity for more complex operations to be performed. And if the bit pattern represents a positive 2's complement integer, shifting it left multiplies it by 2. So we can take a look and consider here this string, right? This binary word, which represents the number 39, shifting it one place left gives us this right here, or 78. So that's really how it happens, is this shifting operation. Now, shifting, when we're working with the left shift, we can see here in the figure kind of how this happens. So a 0 enters into the vacated last significant bit position, and the bit shifted out of the most significant bit position is recorded into the computer's carry flag, right? This carry flag, we can see here kind of represented by C, is a little storage area. It's 1 bit of memory so that the computer can keep track of the state. So let's take a look at this other example here. So let's say we have our negative 29, and it's shifted one place to the left, and we get negative 58. And so we can think about how this carry operation takes place. And then let's talk about how we would shift a number to the right, because this is ultimately how we would divide, right? So we shift left to multiply, we shift right to divide. Let's imagine we have the binary representation for 12, which would be 0, 0, 0, 0, 1, 1, 0, 0, right? 12. If we shift that 1 to the right, we would get 0, 0, 0, 0, 0, 1, 1, 0, which would be 6, right? So shifting a negative number to the right requires some special attention. If you were to apply a simple right shift to the negative number, right, which would start with a 1, you may shift over and put a 0 in that place, which would be incorrect because it's then positive, right, when interpreted by a 2's complement value. So in order to maintain the sign of a 2's complement number, the sign bit is replicated when it's shifted right. And so if we had like the binary representation for 30, which would be 1, 1, 1, 0, 0, 0, 1, 0. Shifting this one place to the right while propagating the sign means we now have 4 ones, 1, 1, 1, 1, 0, 0, 1, which is equal to negative 15. So let's think about, why does replicating the sign bit work when dividing a 2's complement number by 2 by shifting it to the right? Because a positive number is defined by a 0 starting position on the left, and then our 1s and 0s. If we divide the number by 2, we would have 2 0s on the front. We suppose we convert that number to its 2's complement form, we would start with a 1 in our numbers, where each of the numbers is the complement of the corresponding value of our original number, right? So when we add that 1 and replicate it on the front, then we can see that our sign bit is going to be propagated in both positive and negative cases, no matter what. Now, this is all I really want to talk about in this section. If you want to dig further into unsigned binary multiplication, high-speed multiplication, some advanced division operations, you're more than welcome to read the rest of the section of 2.5. But this is a little more complex than I would like for an introductory computer architecture course. So I am going to hop right ahead to section 2.6 on floating point numbers. So having had a look at integers, because so far we've only talked about integers in performing our arithmetic, now we're going to talk about floating point numbers. So the arithmetic of real numbers, because real numbers are that set of all rational and irrational numbers, and floating point arithmetic lets us handle the very large and very small numbers found in scientific applications, as opposed to maybe financial or commercial calculations, because we're not dealing with numbers of such precision. So unlike integer arithmetic, the results of a floating point calculation are not generally exact, because the result of a floating point calculation on one chip may be different to the result of a floating point calculation on another. So floating point arithmetic does not always yield exact answers. We'll talk a little bit about the pitfalls that programmers need to be aware of. So let's talk about storage. A computer with an n-bit word length is capable of handling unsigned integers in the range of 0 to n to the 1, or 2 to the n minus 1 as a single word, right? Because no matter what our n-bit word length is, that's what our single word is going to hold. Larger integers can be created by chaining words together. So for example, a 32-bit computer could work with 64-bit numbers by concatenating together two 32-bit words, where one is the upper half of the 64-bit value and the other is the lower half. Now, scientists and engineers frequently handle numbers that have an immense range of values, from, let's say, the mass of an electron to the mass of a star, right? Extreme ends. And such numbers are often represented and processed by means of floating point arithmetic, because the binary point is not located at a fixed position in the number. So a floating point value is stored as two components. We have a number and a location of the binary point within the number. And we sometimes use this term radix point to avoid having to worry about whether we mean decimal point or binary point. So don't get too confused on the terminology. We'll also see floating point termed scientific notation, right? Because scientists use it to represent large and small numbers. So again, don't get too hung up on the terminology. And then we can see here a binary floating point number is represented by the mantissa times 2 to the exponent. So let's take a look at this notation. If, for example, we have this number, right here. It could be represented like this, where the significand, right, and the exponent of 5, which is our 8-bit binary arithmetic, right? And these days, right, the term mantissa has been replaced by significand. Again, don't get tripped on the terminology, to indicate the number of significant bits in a floating point number. And because a floating point number is defined as the product of two values, a floating point value is not unique. So over the years, systems have been used to represent the significand and the exponent of floating point numbers in computers. Back when we were doing this in the 1970s, the standard means of representing floating point numbers rapidly replaced most of our system-specific formats. So going back to standards, right? We had the IEEE 754 floating point standard. This was the format for floating point numbers that provides 3 representations: single precision for 32-bit numbers, double precision for 64-bit numbers, and quad precision for 28-bit numbers. And this is the standard by which computers now use and normalize floating point numbers. So normalization allows the highest available precision by using all of our significant bits, and it takes full advantage of the available precision. So for example, an unnormalized 8-bit significand has only 4 significant bits, whereas the normalized 8-bit significand has 8 significant bits. Now again, I don't want to get too in the weeds with this, but it's important to understand we have this standard for the IEEE floating point formats, and we can see here in the figure that this specification gives us the specifics for basic and extended floating point formats, and we can support a limited set of arithmetic operations. So we can get add, subtract, multiply, divide, square root, remainder, and compare. And then in a really important concept in the IEEE standard is the NaN, N-A-N, where the N's are capitalized, the A is small, which stands for not a number. A NaN is a special entity provided by that IEEE standard. It permits the representation of formats that don't fit in the standard, and the use of NaN is pretty system dependent. Now, there's a little bit of confusion often amongst systems developers where NaN and null are confused for each other. And they're definitely 2 different things. Null is essentially the representation of nothing, an absence, a black hole. There's nothing there. I have no value. NaN means that it's not a number that fits into the IEEE floating point format. It doesn't mean that it's nothing. It just means it doesn't fit the standard. So it does actually have a value. It's not null, and we should not confuse the two. Now, as I've previously said, most of what comes next in the book is way out of scope for what we're trying to accomplish in this introductory course. If you would like to read more about floating point mathematics, error propagating, generating mathematical functions, doing like floating point arithmetic, by all means. But we're going to jump ahead to section 2.9 on computer logic. Because as we understand, and again, I just want you to understand at the basic level how these operations work inside of the microprocessor, because really, well, I know that you're not performing these operations, and it does not, like in your mind right now, probably make sense of how you're going to use this information. However, it's foundational to understand what we're going to talk about next. And so understanding at that fundamental level about the bits, about the bytes, about the words, about the operations, understanding the signed versus unsigned as a software developer is important so that you can avoid errors in your code when we're working with numbers and understanding things like precision. Now we're going to talk about computer logic. So how does this work, right? Because at this point, it's probably pretty nebulous. You think about this microprocessor and these binary numbers, and we've talked about voltage, but then how does it work? So here's where that comes in. We're going to turn our attention now to gates. Gates are essentially the very stuff that make computers. So computers are constructed from two basic circuit elements. We have a gate and we have a flip-flop. Extremely technical terms. These are known as combinational and sequential logical elements. So a combinational logical element is a circuit whose output depends only on its current inputs, whereas the current output from a sequential element depends on its past history as well as the current inputs. So a sequential element could remember, right, its previous inputs, and it's able to use a memory element, whereas a sequential element themselves can be made from simple combinational logical elements. And we're just talking about circuits. The practical significance of gates is that they're very cheap, right? And this, hopefully you understand at this point, right, why we do things the way that we do them. And it has to do with cheap manufacturing. And with integrated circuit technology, we can put millions of gates on a single silicon chip. So it's easy to build digital systems composed of millions of gates when we take this bottom-up approach to digital systems and make it all depend on something, right? That single gate can now turn into several gates, which creates a functional unit, and then these functional units are all put together to make a computer. And the digital circuits that we use all goes back to just Boolean algebra, right? And it allows us to analyze circuits containing gates and enable circuits to be constructed in a very simple form. And I'm not going to dive deep into the algebra because really this course requires only kind of an overview, but today's engineers don't even employ classic techniques of Boolean algebra to design complex digital systems because they employ computer-aided design software tools that turn algorithmic expressions directly into circuits. So it's not even beneficial to teach that anymore because we're not using it. So going back to our binary system, right? Digital computers are binary systems that use two symbols, zeros and ones, false and true, low and high, on and off. The physical representation of these really breaks down into this idea of gates. And it's not widely appreciated outside of the engineering community that there are more than one type of silicon chip. Several different technologies are used to manufacture digital devices, and we speak of a gate as belonging to a specific logic family. Each of these families has its own characteristics. Some are faster than others, some are cheaper to manufacture, some use less power, some are less sensitive to radiation, right? Great for space. And as time passes, some of these families become more or less popular, or we have designers that build new families that are introduced to reflect advances in technology. And today, logical elements operate on voltage as low as 1 volt, right? Which you think about power usage today, like most cell phones and stuff, like we use like 5-volt power supplies. Now, I don't suppose that any of you have had any kind of foundational course in electronics or electronic circuits, or that you have any idea what I'm talking about. So we're going to approach this from a very introductory stance. For those of you who maybe have, awesome. But let's talk about logical values. So 2 fundamental conventions are used to describe logic systems. One is positive logic, and the other is negative logic. And throughout this course in the text, unless explicitly stated, we're using positive logic, which is where the logical state of 1 is the electrically high state of a gate, right? We also call this the true state, in contrast with the low state, which is the false state. So each logic state has an inverse or complement that is the opposite of its current state, right? The complement of a true to 1 state is false, or 1 and 0, right? Vice versa. A signal can have a constant value or a variable value, right? It's not just flipping on and off all the time. If it's constant, it always remains in that state. Whereas if it's variable, it may be switched between 0 and 1. So our signal level, right, high or low, that causes a variable to carry out the function suggested by its name is arbitrary. If a high level causes the action, the variable is called active high. If a low level causes the action, it's called active low. So if an active high signal is labeled stop, the high level will initiate the action. And if the signal is active low, stop, a low level will trigger the action. So just some clarification, right? These terms that we use when we talk about gates. We're just talking about different states brought on by either our high level or low level, depending on how we've assigned that value. All right, so let's talk about gates. All digital computers, it does not matter which type, are all made up of 3 types of gates. This is the AND gate, the OR gate, and the NOT gate. And maybe you immediately connect some dots here with some fundamental programming concepts to understand how when we write software, we're kind of directly translating what we want to have happen inside of those gates. Now remember, we have the flip-flops. Flip-flops can be constructed from gates. All computers can be constructed from gates alone. And so when we talk about our fundamental gates, right, we look at our figure here, this black box with 2 inputs. A and B, right, are inputs into the box, and a single output, which is C. So this device takes 2 logic values at the input and produces an output that depends only on the states of the inputs and the nature of the logic element. At any time, the inputs and outputs can only be in one of 2 states, 0 or 1. Right? And so this is where we get into thinking about those different states depending on the type of gate. So let's start with the AND gate. And you can see here the truth table. Hopefully you're familiar with truth tables. Really, we just break down all of the various scenarios that might happen in this logical AND gate for our inputs and our outputs. So an AND gate means that in order to get a true value or a false value, both inputs have to be true or false. So let's take a look at this, right? We have our inputs, A and B, and A and B equals C. So if they're both 0, then the output is 0. If we have 0 and 1, it's still 0. If we have 1 and 0, it's still 0. And the only way to get an output of 1 is if both are 1. We can see this here with a 3-input gate, A, B, and C equal D. That again, the only way to get an output of 1 is if all inputs are 1. Let's contrast this with the OR gate. And hopefully you can see here, there we go. Hopefully you can see here that this logic and an OR follows the exact same thing that you've learned in your programming course, right? Like whatever introductory programming class you took, you learned about if statements, logical conditions, and compound conditions. And so with these compound conditions, right, ands and ors, we learned that with an and, both or all of the conditions have to result in the same result in order for the output to be that result. In an or, if either one or more of the inputs are 1, then the gate is 1. So if they're all 0, we get a 0. If one of them is 1, we get a 1. So if B is 0, A is 1, 1, B is 1, A is 0, 1, all ones, 1, right? Hopefully that's not unexpected. And we can compare our truth table for AND and OR gates to make sure that we understand the logic here. So our third gate is called the NOT gate, or sometimes called the inverter, right? It's the simplest of all gates. The inverter or the complementer, it has a single input and output. Its output is the logical complement of its input. So you give it a 0, and then it gives you the opposite. And you give it a 1, and it gives you the opposite, right? Vice versa. So, hopefully that's not outlandish in terms of logic. Hopefully a little more clear than what we've been talking about in terms of arithmetic. But hopefully you understand where I'm coming from in that we have to understand some of what I've been talking about in order to get to this point. So having been introduced to the 3 basic gates, now we can point out that any combinational logic of a circuit can be constructed from our AND, OR, and NOT gates. And a circuit can be represented in one of 2 forms. So here we're looking at our figure of our sum of products circuit, where the input variables or their complements are used to produce terms by AND gates. So these product terms are ORed together in a single OR gate. And we can see how we can just take these gates and combine them together to create essentially a circuit. Something that takes in an input, does an operation, and produces an output. Now we do have this concept of derived gates. So we talked about how there's just 3 gates from our basic gates, but these derived gates kind of build upon the logic of our basic gates. They're used extensively in digital circuits. They have their own symbols, but they're the NOR, NAND, and exclusive OR. So we can see here some logic, right? A NAND gate is an AND followed by an inverter. A NOR gate is an OR followed by an inverter. And an exclusive OR, which you see as XOR gate, is an OR gate whose output is true only if the input is true. So we can see the truth tables here and how this logic is slightly different, but allows us to change the outcome in a way that produces the results that we need inside of our circuit. So here's an example of constructing an exclusive OR circuit from our AND, OR, and NOT gates. So you can construct a circuit out of any of these types of gates and inverters and whatever you need in order to get the result that you want, right? And ultimately, several gates interconnected create a circuit, and all you have to remember is that the output of a gate can be connected to the input of one or more gates, but you cannot connect the outputs of 2 or more gates together. It is the output of the gate that drives anything. Now, the book has several examples of digital circuits, right? We can flip through and look at circuits with multiple types of gates, look at the truth tables for these. They talk about inversion bubbles, different types of adders. So if we want to get the sum. So walking through these and looking at some of these examples, I highly recommend take the time to walk them through, read the descriptions, right? They've got a bunch of different kinds, adders and subtractors, etc. We are going to jump ahead, right? So I'm not going to walk through all of these. I would definitely recommend that you skip the section on sequential circuits for now, as this is, again, pretty far out of scope for an introductory course. Gets into timing tables and sequential operations and Carnot maps and a lot of stuff that, we are not going to cover in this course. But we're going to jump all the way to our final section, which is 2.11 on buses and tri-state gates. And so this section talks about, some of the circuits that are covered through the book. And we can start to really maybe understand how a computer operates by moving data between registers and by processing data. And, as you worked through the examples in the book, right, they talk about building this out of flip-flops and constructing complex systems like several registers and things like that. But we've talked before about buses. And that's really what I want to get at here with the concept of a bus. And we've also talked about registers. So buses are those communication lines, right? How data moves between all of these places in the computer. And registers being those memory locations where we can store a word. And now we can put things together, right? And show how simple operations can be implemented with our collection of logical elements, our registers, and our buses. So we can look at this little system here that's constructed, taking a simple 4-bit binary code, which is placed into 4 separate registers, 0 through 3, and look at the action that needs to be carried out, and look at how this demonstrates when we move and take the 4 registers, the data goes onto the bus, we create this simple functional unit. We have move instructions, which allow us to tell the data, right? One of the simplest computer instructions that tells the data to move from one location to another. And if we think about this in a high-level language in our programming languages, this is exactly what happens if you say, take variable y and equal it to x. We're just copying data from one location to another. So if we execute this move, then we can move this data. We have different data sources. We put the data on the bus, fed into the D inputs of all the registers. We have the 2-bit destination code, so it knows where it's going. We talked about those clock signals being the heartbeat of the computer. So it moves on the clock signal. And the AND gates in this decoder are enabled by that common clock signal so that the data transfer doesn't take place until everything is ready. And then we can extend this system further to include multiple buses, an arithmetic unit, a logic unit, all the things that are covered in this. And then you can really start to see how a computer does its job. This is what's going on in that microprocessor. This is what's going on in that chip. So hopefully, in summary, right, to wrap up chapter 2, we understand that computers are this 2-state binary system that we use to represent information. And we do this because it is the most cost-effective way of doing things. We looked at how numbers are represented as both unsigned and signed integers, how modern computers invariably use the 2 complements notation, and we looked at the representation of how floating point numbers work and talked a little bit about scientific calculations. this gets a little in the weeds of the math that we wanted to cover. So we didn't cover all of those sections, but we got to where we could demonstrate our digital circuits constructed from our basic gates and then our derived gates, and how any combination of these can be used to create a digital circus. A digital circus. Right? The purpose of this section has really been to give you, the student, an insight into the underlying logic of computers. Now, modern computers are not designed at the gate level because software is available that allows systems to be described in kind of like high-level terms, right? We think of like C-like languages. And it directly creates logic circuits from those high-level specifications. But digital systems, essentially, this is how it still works under the hood. Like, we have not gotten away from this. We've just gotten to the point where we can put hundreds of these on one chip. So the important logic element that we introduced here at the end of the chapter, right? We talked about sequential and combinational circuits using gates. We talked about, previously the bus and the register and things like that. So now you can start to see how all of these things tie together to enable us to have this circuit that performs the operation. We have our inputs, our outputs, our memory elements, and how that all goes together in our computer to transfer our data and do our operation. So at this point, hopefully we feel like we have a pretty good idea of what goes on inside of a computer, why this idea of binary is important. And from our standpoint of a software developer, no matter what language I'm writing in, I know that the computer does not read that. It's translated into what the computer does understand, and this is how it's executed. And as a software developer, like starting to understand this difference between signed and unsigned integers, the choices of data type, precision, accuracy, errors, overflows, how it all relates to me and the code that I write. And then as I start to think about my code maybe being more efficient or more effective, I can really understand at a fundamental level the operations that are taking place inside of that microchip, inside of that processor, so that I can make better choices that allow my code to be better. So this has been the end of chapter